Let's take a look at the meaning of dy by dx, or the derivative, which is slope. And if we look a little bit closely at it, dy by dx, so I've drawn a little picture here, it is the slope of the original antiderivative function f of x, and it is basically the slope function. And dy represents a small change in the original f of x function, which we are going to describe as the antiderivative. So if dy by dx is the derivative, the f of x, or the y, is a function that it came from, so we're going to call that the antiderivative. So dy by dx is slope. dy represents small changes in y, dx represents small changes in x. And dy is a small change in the original equation y, so it means a small change in the antiderivative. So that's what that dy means in the graph. It's a small change in the original f of x function. Okay, so we've been using delta x, but we can, if we let this go infinitely small, it becomes dx. So dx implies that delta x is going to 0. So we have dy by dx is our instantaneous slope, or f prime, and we can algebraically rearrange that expression into, so I can multiply both sides by dx, and when I do that, I'm going to end up with dy is equal to f prime dx. So the small change in the antiderivative function is equal to f prime times dx. Now, if you recall, when we talked about area, we're talking about the f prime graph, or the height of the f prime graph, times the delta x. Well, that means then that this is our height, this is the width. So that means that this dy must represent the area under f prime. So that's what we've been looking at. We've been looking at area under f prime, and that dy must mean that the area under the area under f prime must be the same as a small change in the antiderivative. So dy, which is our area, so I'm just going to write it like this. So my dy is small change in the antiderivative is also equal to the area under the derivative. So I'm just going to point to this. These are all equivalent. A small change in the antiderivative is equal to the area under f of x. So one of those rectangular bars represents a small change in y. So in looking at the summation notation here, the sum of all those f prime times dx's, okay, all these f prime by dx's, this is the sum of all the areas. This also must mean that that is the sum of all the changes in the y. So the sum of all the area pieces represents sum of all the changes in y. Well, we can kind of say, well, that isn't that to do with y, the antiderivative? And this is what we talked about at the very beginning. That area under the curve has something to do with the antiderivative function. And that is absolutely true. We can show it by algebra. We have equivalent pieces that we can make this conclusion with. So if we take a look at the next part here, the y represents, because the y represents the antiderivative, or the original function, where we actually generated our f prime function, we can relate this area under the f prime graph And this sum of f prime times dx, or area, sum of all the areas, and that must mean that it is the sum of all the changes between whatever our bounds is. So every single rectangular bar is just a small change. If we add up all those small changes, that represents the net change in the y values from the starting point A to the ending point B. So that's really important. So that's what we're going to claim now, is that the sum of all those dy, all the rectangles, I'm going to write that here, the sum of the rectangles, the sum of the rectangular areas is equal to a net change in the antiderivative function. Okay, so when we consider the original graph of f of x, the antiderivative, and the derivative function f prime of x, is it reasonable to say that the area under one graph is related to the y values of the other graph? And the answer is absolutely yes. They are very much connected. In fact, they are essentially the same thing.